Okay, so let's start. So, any questions? Uh, Normal lecture, I would begin with this one-liner just to ease out while I've wiped the board clean, and it also helps in focusing and bringing attention to the subject matter. But I guess I have not been doing this in this online session because there is no board to wipe clean. So, any questions so far? Whatever we have discussed. Okay. uh, how about taking up a problem? Today I will discuss something about again extending our discussion on ductility and curvature ductility and displacement ductility, and how those influence our design recommendations, and how those design recommendations come about. I mean, where do they come from? But eventually, as they say, proof of the pudding is in eating. So all these discussions have to result into a valid structural design. So nothing better than working with a particular problem to work out the complete design, starting from the first principles, starting from ground zero, so to say. So what we will do is we will take up a example frame and try to design it with complete details, using different aspects of that are required, and end up with our calculation, and come up ending up with the construction drawing, good for construction drawings. So that will complete the entire process, cover the entire process from analysis to design of the complete structural frame. So and in that respect, I would really go for I would like to go for using the plastic method of analysis, as we had initially, you already have experienced, dealt with it to some extent while we were while we were discussing about the capacity design approach, and why beams, hinges in beams are more important or better than development of hinges in the columns, and why it is a better structural performance. And in that particular example, we looked at the plastic analysis and criteria for how that strong column weak beam criteria came about. So that can also be used. The plastic analysis is a very, very handy tool which only requires a simple back of the envelope calculation and work out what is the collapse load, and work out what is the capacities that are required and how to design various capacities. What is the how do we what needs to be done, and how to design the section accordingly. proportion the section accordingly. And that really, I mean, you are not at the mercy or not constrained by any software tool or so. So you can actually now work out the analysis, and even if you do not have recourse to any sophisticated analysis software, right? So we'll try to do that, but uh, before we come to that, let us finish this discussion on ductility. So as I said, displacement ductility is much smaller than curvature ductility. Now why is that? And just to ensure, just to make sure you understand what is the curvature, we are talking about curvature ductility of the curvature of the cross section, the section rotation per unit length. Per unit length. So if I look at the strain diagram in this cross section, so according to Euler-Bernoulli hypothesis, this is the curvature. Right? And what I mean, in case of plasticity, if the steel begins to yield, then obviously this has to extend, and this can only happen by, okay, not coming up very clearly. By shifting, upward shifting of the neutral axis. Right? The strain in the concrete is also going to increase, but not so much as the strain in the steel. So this will be shifting upwards, neutral axis depth, and curvature will keep on increasing. Now moment curvature relationship, as we discussed earlier, so typically it would be something like this, and you model it using a bilinear model. So this is the idealized elastoplastic bilinear model, and this is the real behavior. Right, so, and this is what we call as the yield curvature, and this is what we call as maximum curvature, or whatever is the maximum deformation at the collapse load. So the curvature ductility is, of course, phi m maximum curvature divided by yield curvature, and I told you about the yield curvature. How do we define yield curvature? In terms of it's at the yield level, it is based on the elastic analysis. So epsilon y divided by the length, so neutral effective depth minus the neutral axis depth, or so phi y is epsilon y divided by d minus x if x is the neutral axis depth and d is the effective depth of the section. So this is for tension yielding. In steel, and if the section is very heavily reinforced such that this yielding is delayed, but concrete reaches its peak stress earlier, so then it is also determined by epsilon, not epsilon y, epsilon c, that is taken as 0.0015. Right, so that's the peak, close to the peak stress that is achieved in unconfined concrete, and after that it begins to crack slowly, gradually. So until you get the ultimate strain of, when the concrete completely gets crushed, is about 0.003 or 0.0035. Right. So this is the yield curvature that is determined, and maximum curvature is of course the at the ultimate load. So usually you will find that it is often greater than 20, and this is when I consider the displacement ductility of the order of 4. So total displacement ductility, again if I define total displacement ductility, is defined as maximum displacement divided by the yield displacement. Now this is the maximum displacement, and I define the yield displacement accordingly. If load displacement curve, if I define this load displacement curve according to the similar, then this will also be like okay, let me draw this separate figure. So typically this is what you look like. What you call as a pushover analysis. So ultimate displacement, maximum displacement, and again something similar idealization that you do. Yield displacement at the first yield. And this for the structural level. Now you can have displacement ductilities displacement ductility at structural level is very different from that at a element level. So while a particular element may be very highly ductile, but the total, when I look at the load deformation curve of the total structure, then the available ductility, displacement ductility of the total structure might be very limited. So that is to say that individual structural element level performance, let's say if I test only a beam or only a column and then show that it is a very good, very highly ductile, and say that this is good for earthquake resistance, this is not enough. Merely examining the uh, performance of an individual element of the complete structure and testing its performance and ductility is not enough to uh, ensure that sufficient ductility will be available at a global level when we consider these interconnected members. So total structure is a whole, is a combination, is an assembly of different structural elements. So beam, columns, frames, uh, walls, and then how the beams and columns are connected together, the joints, beam column joints. So they all, and the flooring system, how they are behaving, how different bays are interconnected, whether it is a rigid floor diaphragm, whether the forces are being transformed faithfully in different bays, or is it according to tributary area, whether it is forces not being transformed, transferred correct as we assume, as we consider. So all those factors determine the behavior of the integrated system. So in the ultimate test, it is the integrated system that is put at test, not the individual elements. So individual elements may independently do very well, but it is essentially a team effort. It is essentially how the different elements which are put together to form the structure. It is that integrated unit, integrated system uh, whose performance is in question. So I will let us just try to develop this analogy, try to understand this by a simple system which is very often used to describe this particular problem of element level versus global level ductility. So let's say a series of links together, right? These are the rings that are interconnected with each other, and out of that, let's say one particular link let's say this is a ductile link, right, and these are all other are brittle links. So there are, let's say, this chain it is being subjected to a chain of, obviously can take only tension. So it is being pulled by a constant force. It's a uniaxial system. So let's say this chain comprises of n brittle links and one ductile link. So n brittle links, their load deformation curve might be like this. So this is for brittle links. For ductile links, for ductile link, it can be somewhat like this. And the combined behavior, so this is for ductile. So you can assume this as a steel links, n number of cast iron links, and one aluminium link, so to say, or mild steel link, and together their performance is something like this. I can say this is series combination. Right? So what is the total displacement? What is the, obviously you can see that this is very highly ductile. Individual element is very, very highly ductile. But what happens when we look at the total behavior? It is ultimate displacement, maximum displacement divided by the yield displacement, right? So what is the displacement at the yield? Until yield point, all the systems are carrying the same deformation, so same force. So they would all be having a similar kind of forces. So I would change this just to make it clear that initial stiffness is same for both. Let's not complicate it too much. So that the initial stiffness is same for both the brittle and ductile links. So when we talk of this yield level, then the displacement in all the links is essentially of the same type, same amount. So when we look at that, so at the yield level, total displacement becomes delta y is equal to n times delta 1 plus delta 2 y. So delta 1 is the displacement or the deformation in the brittle link, and delta 2 is the deformation or the stretch in the ductile link, right? So delta 2y, that's the yield displacement of the delta 2 at which it yields. So this is the total displacement at the yield point, and we assume at this particular point delta 1 is same as delta 2y at the yield of ductile link. So this is essentially equal to n plus 1 delta 2y. Right? And then after once this deformation load increases, then the deformation is of course going to keep on increasing. So delta m is equal to n times delta 1 plus delta 2. Right? So most of the deformation after this point, the deformation is going to concentrate here, isn't it? It is the force, if you keep on applying force, this particular element will begin to flow, and it will just not, the force is not going to be transferred much. I mean, it is, the system is not going to take much of the force. So that's why you will see very, very small slope of bilinear hardening. So the brittle other elastic link elements really have very, very small contribution to make. Most of the deformation is actually taken care of, is absorbed by this ductile link, and it keeps on flowing. So that's what most of the deformation is here, and this deformation is almost same as delta 1. Okay, I'll also say delta 1m is almost same as delta 2y. Nothing much, doesn't change much. Beyond the yield. Displacement of ductile link. So total displacement now becomes n times delta 2y plus delta 2m, and then when I combine these two and figure out what is this displacement ductility, so n times delta 2y, because each of these n number of links will keep on will move by the same amount. So because all of them carry the same force, so they will have this displacement plus delta 2m. That's the maximum displacement in the ductile link, and then n plus 1 delta 2y. So this gives you n plus mu divided by n plus 1. Right? So what does it mean? So this is again, if I do this, so this is n by n plus 1 plus mu by n plus 1. So if this is very highly ductile, individual element, what I am trying to bring out in this calculation is, even if this is very highly ductile material, let's say displacement ductility of the order of mu of the order of let's say 20, right? And if there are, let's say, 10 number of elements, 10 is a very small number in a normal structural system. We are talking of hundreds of such elements, individual elements, beam, column and walls, right? So let's take 100 just to be just to get an idea. So for and mu element or mu element level is 20. So mu displacement ductility, global displacement ductility is, this is approximately 100 by 101. So this is approximately 1 plus 20 divided by 101. So this is 1.2. So now you can appreciate the difference between the integral behavior and the individual behavior. So even if the individual element, one particular element might be very highly ductile, it may have ductility of the order of 20, but it is the integrated action that is more important, that is actually put to test. And when it is integrated with a system of non-ductile material, then the total displacement ductility available at the point of failure is only is very small, in comparison to the individual ductility that the elements may exhibit. And similar thing actually works for curvature ductility. Curvature ductility can be very large, I mean just as this element, because when we do that ductile detailing provisions, then the confinement, the strength of the confined concrete increases considerably, and then it is the section is able to achieve very large curvature ductility, right? And that curvature ductility is necessary. We need to achieve that high curvature ductility in order to get adequate displacement ductility. In order to get an adequate displacement ductility of the order of 4 or 5, you can imagine, I mean this maybe 100 was not a good number, so let's say I would just say n is equal to 10, so 11, so this would be about 4 approximately 4. No, 3. So for this particular simple system of 10 number of elements, 10 number of brittle links and 1 ductile link, if the ductile link has a ductility of 20, then the complete assembly has a ductility of about 3. So when, I mean if I look at this problem in a reverse way, if I am to work with a system of assemblage, and I know that I can have ductility in only a few locations, in only a few elements, then I need to make sure that I get sufficiently high ductility values. I am able to generate sufficiently high ductility in those designated elements and in those designated locations in order to get some reasonable amount of ductility for the entire assembly, right? So in order to get the displacement ductility of about 4 or 5, it is very often required that I need to develop, I need to generate curvature ductility of the order of 20 to 30, right? And these kind of curvature ductilities, if you look at the curvature diagram, this kind of curvature ductility where you have ultimate curvature very large and going beyond the much beyond the plastic curvature and developing the plastic hinge which will lead to rigid body rotations. So those kind of curvatures are only possible when you adhere to very specific, very stringent requirement of concrete confinement, because there is no way we can have very large curvature ductility unless we have commensurate increase in the concrete strain, which can keep up with the elongation of the steel, right? So that is only possible when we have very well confined concrete, and that is why, I mean, confinement requirements, concrete confinement requirements for the lateral ties, they actually are more stringent and more critical than those that we encounter on the basis of merely shear resistance. So although we need to check for shear capacities as well, but in general you will find that confinement requirement that arise from the need to confine concrete in order to get very high curvature ductility is generally much more critical than the shear resistance requirement. So having said that, we come to then how do we decide about this? I mean, how are those requirements about the spatial confining reinforcement, or how do we decide whether the process that we have developed, or design process that we have developed, is adequate for the practical purposes? Because all this that we are doing is just some kind of assumption. I mean, you can see we are making some kind of simplifying assumptions in order to get at these numbers. Working with actual exact numbers is going to be very, very tedious and complicated, right? So we are deriving these numbers on the basis of some assumptions, and there are assumptions all along. So how do I ensure, or how do I make sure that whatever I am doing will actually make the design or the structure that we put on the ground actually safe? So how to assess the adequacy of design provisions? Because now we are arriving at something very different from what you have been dealing with so far in your design courses, right? Emphasis is now on the global or integrated action of an assembly instead of elements, I would rather say structural elements. Right? In gravity load design, you only pay attention individual element capacities are considered. Right? So you For a gravity load design, simply you carry out the analysis, find out what are the actions on the beams and the columns, bending moment, shear force, and work out whatever is required, and the moment capacities are provided in the individual elements, and that's how you define the cross section, that's how you define the reinforcement details in the members, and get done with it. But in case of earthquake resistant design, it is the integrated action of the assembly of structural elements. Individual elements may be very ductile, but how they perform when combined together, that is very critical, because it is the combined action of the complete structure that is that has to withstand the earthquake, not the individual element, and that requires very stringent requirement and very stringent test. So whatever is done, how do we ensure that, let's say we have a column and a beam. Right, so column, beam, connection. So now obviously you will have, if it is a reinforced concrete, what we are discussing right now is equally applicable for steel as well as concrete. So you can just say this is column and this is beam, and it can be anything. It can be reinforced concrete, it can be a steel system, whatever. So what is done is, obviously you cannot test a full scale structure to failure. I mean, remember, when we talk about the ductility, we are actually talking about taking it to failure, taking the system to ultimate load. So total ultimate load capacities of the structural and global structural system is only tested by Mother Earth. We do not have the experimental capacities to test the full scale structures to failure, and there is no system in the world which can test that. It's not that it cannot be built, but it is not required and it is not economical. The larger the test facilities are, it becomes they are that much more expensive to build and that much more expensive to maintain. So it is not a very prudent call to develop a very large scale facility which will with a target capacity which will probably be never be required. And moreover, it is often possible to figure out or infer very useful information based on the sub-assembly test. For example, this beam column connection. So if this is a sub-assembly, right, and I can test it. Sub-assembly testing, because then it is only a very small component, a small sub-component of the complete frame, and it is possible to test this sub-assembly to failure. To collapse, or I wouldn't say collapse, to ultimate displacement, or even not ultimate displacement, to testing for maximum target displacement. Right. So what is done is testing assembly. I mean, once you come to the campus, you will see the experimental facilities, and then I'll explain how these testings are done. But what we are doing here, I mean, what I explained, that we need to develop very high confinement details so that concrete can sustain much higher strain, and it can generate reasonably large curvature ductility, so that we can get a reasonably sustainable amount of global displacement ductility that can be harnessed for inelastic deformation to withstand very severe earthquakes, which may occur only very rarely, right? So it is not prudent to design elastic with for no damage for a earthquake which is very severe and which may not even occur during the lifetime of the structure. So it is very unlikely that a very strong earthquake will occur and will test the structure during its lifetime. So we design to sustain damage, but then those damages have to be in a form that can be accommodated with inelastic deformation through the ductile behavior. And for that we have some specific ductile detailing provisions that you can refer to in the IS code 13920, which prescribes certain amount of detailing, certain amount of reinforcement detailing, and of course IS 800 also prescribes, new version of IS 800 also prescribes the suitable detailing for ductile steel frames, right? So and those we presume that by following that we will get the required ductility, or that will provide adequate ductility in the system which will see us through the earthquake. But that confidence actually comes from experimental evaluation. So what is done is for the maximum target displacement, so that is delta M is equal to whatever is the target ductility multiplied by yield displacement that is determined from the target, what is the elastic limit that we have, and this target maximum displacement, this assembly, so far we are only talking about, I mean, all the load deformation curve that we are discussing here, they are all you will find I'm only plotting them monotonic, but actually you have to deal with cyclic loading, right? So in a typical system, what I would do is put a at the midpoint level force or displacement. I can apply these actuators. So the actual system is like this. Let me just because columns are typically, as I said, we don't allow hinges to form in columns, so the potential hinge location is somewhere here around the distance of D from the column face. So that is the potential hinge location. Right? That is where we want hinge to develop. We don't want hinge to develop at the column face, exactly at the column face, because that will jeopardize the column integrity, and it will convert it into a mechanism, portal mechanism, and it will lead to collapse of the system. So we wish the hinge to develop at a distance away from the column face, and to test it, column, of course we do not allow it to sustain any damage. So in the testing, what is done is we have a very strong system of reinforced concrete floor and wall. So this is what we call as strong floor. This is what we call as reaction wall. On this strong floor, we mount this specimen, and these are held together just so that this does not slip. So they are bolted down to the strong floor, and then this is the actually column. So during test, what we are doing here is the testing the capacities of the beam, behavior of the beam, because that is where the damage has to happen. And then there are these actuators anchored, and these are attached to the beam. Hydraulic actuators. So with these actuators, they can actually operate can be operated in load control or displacement control. That is, I can specify either how much force to apply on this specimen, or I can control how much amount it has to move, right? So both, so either load control or displacement control. So what we are doing here is we generally go for displacement control. So we know what is the maximum displacement that we need to have in this system for the given ductility that we are aiming for, right? And so this is the structural ductility, and multiplied by the yield displacement, and that gives me what is the maximum displacement. And then I apply 4 cycles of this maximum displacement so then I will apply so how many? 1, 2, 3, 4. Okay. So these are the 4 cycles. This is 1 cycle, this is 2nd cycle, this is 3rd cycle, and this is 4th cycle. Right? So there are in all 8 load reversal. So this is one maximum load, negative maximum load, second positive maximum load, second negative maximum load, and so on. So now this is a cyclic behavior. So we are testing the capacity in both the direction for the different directions of the earthquake motion, right? And when we do this for the maximum displacement, so this is delta m and this is minus delta m. When we do this, and obviously there is a feedback system which will monitor all the complete load deformation curve. So I can also plot what is the uh, load deformation happening. So complete hysteresis is available because it's a cyclic. So now I will have the complete uh, displacement. So similar kind of thing. So this kind of hysteresis is generated. So when we find that after these 4 cycles of displacements, maximum displacement, 4 cycles of maximum displacement cyclic loading, the capacity of the structure does not degrade by more than 20%. So the smallest deformation, this is, if this is P max, then this has to be 0.8 P max. If this is achieved, then we would assume that the adequate resistance is there, and the sustain structure will withstand, will be able to withstand the target displacements with adequate safety margin. Of course, that requires, because you will find that this is a very stringent requirement. You will not be able to achieve this unless there is sufficient strength in the beam column region is strong, and this does not, damage doesn't happen here. If the damage happens here, then obviously your load carrying capacity will drop down very dramatically. Right? You can imagine if this thing gets damaged, then it's like a hinge that is developing, and in that case there would not be any resistance to the lateral force, and effective load that will be resisted will be effectively zero. So there will be no resistance to the lateral force, the cyclic loading that you have, and therefore this is a very good measure that the entire integrated action of the structure is being ensured if after these 4 cycles of maximum deformation the force level doesn't reduce by more than 20%, and that is a good indication of a design objectives being met, and that is how those recommendations find their way in the design codes. So I'll stop here. So any questions?